All right, welcome back. So we're gonna try another example here to be able to analyze the graph using the increasing and decreasing concavity as well. So let's begin. So just a FY note, a note, special note. Use DNE if the answer does not exist for any characteristics below. So we're given this function y equals the quantity of x squared minus 1, everything to the third power. And so we're asked to find the domain of this function. The domain of this function is going to be all real numbers. So from negative infinity to infinity. The reason is because if you expand this, right, then this is just going to give you create you a polynomial, and the domain of this will be the domain of polynomial functions is all real numbers. All right, so let's find the x-intercept and the y-intercept. So as we mentioned before, the x-intercept can be found whenever y equals 0, and so you're finding what the value of x will be. So take your function, so replace that with 0. So this is your y, so that equal to 0, and solve for x. To solve for this, we would say, okay, well, the only way that this is going to equal 0 is because you're taking the power of it, is that the inside happens to be 0. You can also argue that you can just take the cube root on both sides of the equation, right? That's another way to think about it. And then from here, you're going to end up adding 1 on both sides. And therefore, we get x squared equals plus 1. And then you take the square root on both sides, plus or minus. So we end up getting x equals plus or minus the square root of 1, which we know is 1. So therefore, it tells us that when x equals negative 1, the value of y is 0. And with the similar argument, when x equals 1, your y value is 0. So these are your x-intercepts. Now let's find the y-intercepts. Same argument. We're looking for the value of y when x equals 0. These are typically tend to be much easier to find because all we gotta do is use the function and replace every x with 0, right? And that gives us negative 1, right? Because 0 squared is 0. 0 minus 1 is negative 1 to the third power will give us negative 1 times negative 1 times negative 1 is still negative 1. So that means the y-intercept is going to be 0 comma negative 1. All right, found the y-intercept. Not so bad. The next one is finding whether the function has a symmetry. And symmetry comes from the back in geometry when we talk about whether the functions are have the same image in respect to maybe a line segment. That means that whether the left side just behaves the same way as the right side. So I'm trying to make it look the same, right? Symmetric means that they're the same, right? These two the same. But that could be in different ways, right? So there's two ways that we can have symmetry in respect to the in respect to the y-axis or in respect to the origin. So well, the way we find this is by doing simply this, right? So if I take back the original function, I know it's in terms of y, but I'm just gonna write it in terms of x. And what you do here is just literally just take the inside and change it from positive x to negative x. And that's always what you have to do, right? That's what the technique that we learned back in algebra. And so replace the function with negative x. And then see what you end up getting, right? And so I explained that what kind of conclusions are we looking for. So if you remember that when you replace something into a variable, you gotta put the parentheses, right? Because otherwise you will get a different answer, right? Not correct answer. So negative x raised to the second power will be negative x times negative x, which will be positive x squared. So you end up getting x squared back, and you still have minus 1 cubed. And so what we end up seeing here is that the end result, right, after you plug in negative x, is exactly the same as the original function, right? You end up getting this the same thing as the original function. That means that when that happens, right, when this happens, this implies that the function has a symmetry, and the symmetry is in respect to the y-axis. The other outcomes that you can get is that you plug in negative x, and the end result happens to be minus f of x. In that case, then this is symmetry in respect to the origin. And then you can also get that negative x does not equal any of those, right? Right. That is not equal to one of those two options. In that case, there's no symmetry. All right, so that was just a side review, right? In this case, what we have is symmetry on the y-axis. Okay, perfect. All right, so let's jump into horizontal asymptotes and vertical asymptotes. All right, so we know that to find the horizontal asymptotes, what we're going to do is we're going to take the limit as x goes to infinity of the original function, which happens to be the limit of x squared minus 1, everything raised to the third power as x goes to infinity. Well, what happens here is that this is becoming very large, and then you're squaring it, and then you're subtracting by 1, which doesn't make any difference, right? You still infinity, and then you raise it to the third power, so this is just going to infinity. Similar argument happens to the limit of the function as x goes to negative infinity. In this case, right, when you plug in negative infinity here, right, well, the square is going to square it, so you're going to have negative infinity, which makes it positive infinity. Positive infinity minus 1 does not make a difference to this, still positive infinity. And then you raise this positive infinity to the third power, it still gives you positive infinity. So because they're both the same, this implies, implies that, well, it doesn't have to be the same, but this means that there's no horizontal asymptote. So horizontal asymptote does not exist. What about vertical asymptote? Vertical asymptote. Well, the vertical asymptotes are found whenever the function is undefined, but we happen to know that this the original function is a polynomial if you expand it. So the vertical asymptote does not exist. Right. Remember that we usually do that by finding where the denominator is 0. So that's not the case in here, right? The original function is clearly a polynomial. The next one is to find where the function is increasing, decreasing. So we know that happens. We have to create a number line, and we use the number line to separate it using the critical numbers, right? Critical numbers are found whenever the derivative is 0 or undefined. Right? The critical numbers are x values. That makes the following true. So let's jump in with that first. Let's find the first derivative. The first derivative of the function, let me maybe rewrite the function up here so that we can kind of follow, so we can kind of follow that much easier than trying to guess what the original function was. Okay, so the derivative of this, which rule are we going to be using? Well, we have a function inside a function. You can clearly see here x squared minus 1 is the inside function, and the power function is the outside function. So we're going to use chain rule, which means bring down the power, leave the inside as it is, remove 1 from the power, and then multiply by the derivative of the inside. Right, so we'll do that in the next one. So that will be equivalent to 3 times x squared minus 1 squared. The derivative of x squared minus 1 is 2x. And so to find the critical numbers of this, we're going to set this equal to 0. And this implies that this is going to happen. This is going to be 0 whenever x squared minus 1 is 0, or whenever 2x equals 0. The 3 cannot equal 0, so we're not using this one, right? And so that implies that in order for this one to be 0, this we can kind of think about, oh, we can just take the square root on both sides, right? And that eliminates the square root, leaving us with x squared minus 1 equal to 0. And this is very similar to what we did up here, right? The same process when we were solving for x squared minus 1 equal to 0. Since it's the same thing, right, we can argue that we're going to end up getting the same answer. For the purpose of time, that's the reason why I'm sort of kind of jumping this, right? I don't want to make this video too long. And then divide this by 2. And this gives us x equals 0. So these are the possible points. These are possible critical numbers. Remember that in this case, because the derivative happens to be a polynomial as well, maybe this is a better, then this is never gonna happen, right? It's never gonna be undefined, so you won't be able to find any x value that makes that undefined. So in order for us to confirm that these are critical numbers, we would need to show that these are part of the domain. But because we know that the domain is all real numbers, therefore we know that these are critical numbers. So even though they didn't ask us for critical numbers, these are sort of kind of important for the process to determine where the function is increasing, decreasing, right? So let me make a number line. We're gonna make we're gonna use -1, 0, and 1. Make sure that these are in the right order. Sometimes students get too excited and they forget that they need to be put in the right order. And what we know is that when x equals -1, your derivative is 0. When your x equals 0, your derivative is 0. And when your first derivative, when x equals 1, the first derivative is 0. So I'm going to go ahead and circle these. And then we're going to test numbers over here, right? -2, any number between -1 and 0 will be -1/2. Any number between 0 and 1 is 1/2. And any number on the right side of this will be 2. So we got a lot of numbers to test, right? So let's see what we have. Let's try that over here, this color. Let me bring this over here. All right, so what we need to test these numbers into the first derivative. So let me look at the first derivative. All right, so we want to be practical, right? We want to make sure that our process is practical and easy, right? So I'm going to take some time to show you guys a few techniques that I want you guys to consider. So for example here, before we jump in and try to test these numbers, think about what we're looking for. All we need to know is whether this is positive or negative, positive or negative, positive or negative, positive or negative, right? We have mentioned that before. But we can look at this, what we have so far, and we know that this factor is positive. 3 is a positive number. And we also know, we can conclude that this number right here with the square is going to be also positive, right? Because whatever that inside is, you're going to square it. When you square a number, you always turn that number to be positive. So all we have here is positive times positive times 2x, right? So that actually makes it easier for us to work with, because all we gotta do is just pretty much, we just almost like made this super easy, because where we know it's gonna be a positive for the first one, positive for the first one, but when you plug in -2 in here, you have negative 2 times a positive 2 would make it a negative. So this whole thing is going to be negative. Same thing here, positive, positive. And then when you plug in that negative 1/2 into the x, negative 1/2 times 2 is going to be a negative number. Then you try 1/2. It'll be positive, positive, and then 1/2 times 2 is going to be positive 1/2 times positive 2 is going to be a positive. So this gives us positive, 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 and then when you plug in 2 for x, positive 2 times positive 2 gives us positive. So what we end up getting here is a very nice result, a very quick result. This will be negative, 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 positive, 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 positive. So that means that your function is decreasing, horizontal, decreasing, horizontal, increasing, horizontal, increasing, right? That's how sort of kind of like how it looks like. And so if we're looking for when the function is increasing, decreasing, then we're going to say it's decreasing from negative infinity all the way to negative 1, and from negative 1 to 0. Right? If you guys notice, it's from here to here, and then you jump from negative 1 to 0. And then for the positive, it's going to be from 0 to 1, and then from 1 to positive infinity, right? That's where the function is increasing. So increasing from 0 to 1, and from 1 to infinity, right? And there you go, right? We have found where the function is increasing, decreasing. That's all they ask us to find. But I hope you guys liked this strategy. Just remember that understanding the concept, understanding what you're asked to find, kind of helps you in the process. Because remember, these are lengthy problems, so you do want to make this as simple as possible for you. All right, so now let's find the local max and local min for these problems. And we see here that we can kind of see that these functions are whether they're going to be increasing, decreasing, right? Here, what was happening in the function? We can kind of see that from the picture here, that we don't actually have something. This is decreasing, and then it levels down, and then decreases again. And so the only place that actually turns around is here, right? Turns around right here. So actually, there's only one possible local extrema, and that is at x equals 0. So x equals 0 happens to be a local allocation. You have a local min at x equals 0, but they are asking us to find the actual minimum, so we're going to find the y value. The y value is the actual minimum, so that will be the local minimum, which will be by plugging in 0 into the original function. Gives us negative 1 to the third power. So so y equals 0, negative 1. So 0, negative 1 is the local min, right? The local min is actually negative 1, but the point where you find it is the point 0, negative 1. All right, so now we're going to find concavity. The concavity is found where the function, and we're going to have to take the second derivative for that. So let's look at the first derivative. Let me see if we can find the first derivative. So what we're going to do here for the first derivative, we can see here, what I'm going to do is I'm going to multiply these two together. That gives us 6x, and then that gives us 6x times x squared minus 1 squared. All right, so that's your first derivative. We wanted to take, to find the concavity and any inflection points, we have to take the second derivative. So we need to take the derivative of the first derivative. Now, because this is a product of two functions, we have to use the product rule. So 6x prime times x squared minus 1 squared plus 6x times x squared minus 1 square prime. All right, so using the product rule, we are going to get this, the derivative of 6x is 6 times x squared minus 1 square plus 6x, and the derivative of this function here is, by using chain rule, bring down the 2, leave the inside as it is, subtract 1 from the power, and multiply by the derivative of the inside. And I'm going to go ahead and just take the derivative of the inside for now. Here is 2x, right? Instead of doing the extra step that I usually do. But for purpose of time, I want to move this problem along. What I would recommend here is, because we are trying to find where the second derivative will be 0 or undefined, it's more convenient to try to write this in a factor form. So I want you guys to really try hard here to factor as much as you can. If you notice, you have two terms, right? That's the two terms, right? Separated by the plus sign. So remember that you can factor if you have any common factors. And we do, right? If you notice, 6 and 6 is there. And then you have an x squared minus 1 factor. You have two of them in here. Here you have one of them, right? We have one of those factors. So what I would suggest here is to factor that 6 and one of those x squared minus 1. And then put a bracket, that way you can kind of see what's left behind after you remove those two factors from those two terms. You're going to remove that 6, so that's gone. You're going to remove one of those factors, so that 2 becomes a 1. So x squared minus 1. Because now it's raised to the first power, I don't actually have to put a parenthesis anymore because there's nothing in front of it as well. We remove that 6 away, and we remove that factor away. So what's left behind? X, 2, and 2x. So x times 2 is 2x, times 2x is 4x. 4x squared. There you go. And then you will simplify this. And you have x squared minus 1 plus 4x squared gives us 5x squared minus 1. All right? All right, so now from here, what we're going to do is we're going to find the possible points of inflection, which I remind you happens whenever this is the second derivative is 0 or the second derivative is undefined. There you go. So that is not going to happen because we know that this is a polynomial, so it's defined everywhere. So the only case that we have is whenever this is 0. So we're going to set this equal to 0 and use a 0 factor property. And this will tell us that, of course, take every factor and set it equal to 0. Now we're not going to use the 6 factor because we already know that's not equal to 0. All right, and solve for x. We already done that problem before in this example, in this video. So this is going to give us, again, plus or minus 1. This one will add 1, and this will give us 5x squared equals 1. Divide both sides by 5. And then you end up getting x squared equals 1 over 5. Take the square root on both sides of the equation to remove that square, to undo that square, plus or minus. This gives us that another 2 possible points, right? So this is the same thing as plus or minus square root of 1 over the square root of 5, right? Because we can separate the square roots with the numerator and the denominator. The square root of 1 is 1. The square root of 5 is very infinite decimal, so we're gonna leave it as is. All right, so there you go. We found the points of inflection. We haven't even found. We still have to use these points to create a number line. So what I'm gonna do here is I'm gonna minimize this here, so I can have extra space. There you go. All right, I think There you go. Okay. All right. So from here, we're gonna maybe move this as well. Okay. Because we need a lot of space here. We need to create a number line and use those numbers that we just used to separate to divide this number line. And the numbers that we have here is going to be negative 1, 1 over negative 1 over square root of 5, and 1 over square root of 5, and 1. All right, so it's a lot of numbers. And so these are the x values. We already know what happens in the derivative, the second derivative for these numbers. They're all going to equal 0, 0, 0, because that's how we found them. So what the question is, what is happening around these numbers? So let's try a number from this side, negative 2, randomly chosen, right? Negative 3/4, 0, 3/4, and 2. All right, so I'm just choosing numbers that are in between those two, and I'm going to go ahead and test them. So what is the actual function that we got to test? Is going to be f of x, second derivative of x equals 2. It's going to be, let's see if I have enough space here. Six x squared minus 1 and 5x squared minus 1. All right, so when you plug in negative 2, the 6 is going to give us a positive. When you plug in negative 2 here, you're going to give 4 minus 1, which is a positive. When you plug in negative 2 there, you're going to get a positive 4 times 5 minus 1 is still positive. So this is a positive. Then when you plug in negative 3/4, the 6 is going to be a positive. Plug in 3/4 in there. That's going to give us negative 3/4. That's going to be a negative number. Because negative 3/4 is smaller than negative 1, right? That's going to give us a negative number here. And here is negative 3/4 squared will give us 9 over 4 times 5. That's 15 over 4 minus 1. That's still going to be a positive number. When you plug in 0, positive 0 squared is 0 minus 1 is negative. 0 squared times 5 is 0 minus 1 is negative. So negative times negative is positive. Plug in 3/4. It's the same situation as what we had before. 3/4 squared minus 1 is going to be negative. And 3/4 squared is going to be 9 over 16 times 5 is going to be 15. No, 9 times 5 is 45 over 4, which is greater than 1. So that's going to give us positive. And lastly, a 2, which gives us the same result as before. Positive times positive times positive equals positive. All right, so this one is negative. Oops. There you go. There you go. There you go. There you go. So basically what we have is positive, positive, negative, negative, positive, positive, negative, negative, positive, positive, positive. And this translation to the function is concave up, concave down, concave up, concave down, concave up. So this is concave up from negative infinity, right? So let me just maybe underline from negative infinity all the way to negative 1, and then from negative 1 over square root of 5 to 1 over square root of 5, and then from 1 to infinity. And then concave down from negative 1 to negative 1 over square root of 5, and negative and 1 over square root of 5 to 1. Okay, and there you go. And inflection points. We still gotta figure out what if we have an inflection point, and by looking at this, we have a this could be this is actually inflection point because there's a change of concavity. This is also inflection point because there's a change of concavity. There's an inflection point because there's a change of concavity, and because there's another change of concavity, this is also going to give us an inflection point, right? So we need to figure out all these values. So when x equals negative 1, your y value is f of negative 1. If we put this in the original function, it should give us 0. So hence negative 1, 0. X equals negative 1 over square root of 5. This will give us y equals f of negative 1 over square root of 5. This will give us, let's see, it will give us negative 64 over 125. And so this will be negative 1 over the square root of 5, negative 64 over 125. And the same argument for x equals 1 over square root of 5. This will give us negative 64 over 125. And lastly, x equals 1. This will give us 0. Okay. Alright, so we found all the information that we needed. Now it's time for us to plot it into our function, into our sketch. So looking back, what we have here is negative 1, 1, negative 1, 1. We'll also have positive 1, 1. Positive 1, 0. We have 0, negative 1 right there. And then we also have those are the critical numbers. And what else do we have here? Critical numbers. Let me minimize local min. We also have critical numbers. The function is decreasing, right? From here is decreasing, decreasing, increasing, and then increasing according to our function, right? But we also have a concave up on the left side of negative 1. So we're seeing something that is decreasing, but a concave up. And then we have an inflection point at negative 1 over square root of 5. How much is the square root of 5? is roughly 2.23. 2.23, and then 1 over the square root of 5. Right, so that's 0.44. So somewhere in here, 0.44, negative 0.44, we have negative 64 over 125. So somewhere in here, we have a inflection point, and also somewhere in here we have the inflection point, right? So those are the inflection points that we found. At negative 1, we also have an inflection point because we changed concavity. So maybe I can use a different color. Right, so let's use a different color here. So we have a concave down, no, sorry, concave up right here, followed by a concave up right here, and followed by a concave up right here, and then followed by a concave down right here, and followed by a concave up right there. Right. So and so all the points are given there. As we said before, let's give the points that are proper here. Negative 1, 0. This is 1, 0. This is 0, negative 1. This is negative, no, sorry, this is 1 over square root of 5 minus 64 over 125. And this is negative 1 over square root of 5, comma, negative 64 over 125. All right, so the idea here is that we are following what we're given, right? We know that it was decreasing on this side, decreasing, and then increasing, increasing, and then increasing, right? But we also have to use the concavity, concave up, right? Concave up right here, followed by a concave down, followed by a concave up, followed by a concave down, followed by a concave up, right? So a very interesting process, right? We are getting all the information and using all the information to help us